Okay, so good afternoon, everybody. So let's continue our class for today. Okay, so actually, we want to continue. Okay, maybe I'm not sure. Maybe today is the last class, or I think we have a next week another last class. I think it's the next week last class. Okay, and on Sunday, so we have a test too. Okay, I've prepared already the questions. So I think it's quite easy, the questions, chapter 6 and chapter 11. Okay, so I just want to update something that for this chapter, we will cover until the single reactions. Okay, so phase rule and Duhom's theorems, as well as multiple reactions for the relationship between the equilibrium constant and compositions. We will not cover this part. Okay. So let's see, we continue from the last class. Okay, so I think we did already this one, and this one about the equilibrium constants we already explained. Okay, so let's see how to calculate the equilibrium constants. Okay, and the relationship between equilibrium constants and compositions. What happen if we increase the pressure? Okay, or we decrease the pressure, increase or decrease the temperature, as well as the reaction is endothermic or exothermic. What happened to the composition? Okay, reactant as well as product. Okay, so what's the relationship between delta G naught and the equilibrium constants? Also, we will discuss here. Okay, so actually, if we want to determine the equilibrium constants, we need to determine delta G naught. So how to calculate delta G naught? Okay, so we recall it back about the Fugasti species in solutions. Okay, as well as for the pure species. Okay, mu is for the uh, chemical uh, chemical potential. Okay, and G naught is a Gibbs energy. So if we do the difference between these two equations, okay, thermokinetic. Okay. Okay, so if we do this one, mu minus with the G I naught, okay, so we can get relationship RT F cap divided by F naught. So that means species in solution, fugative species in solution divided by pure species lah. Okay. So from these equations, okay, and substitute into the criteria of chemical reaction equilibrium. If you remember, in equilibriums, the chemical potentials, okay, equal to 0. Chapter 11. Okay, you have to remember that. Gibbs energy also 0. Okay, this one is for the mixture. Okay, regarding on the chemical potential. Okay, so and we rearrange all the equation, we can get the expressions. Okay, this is the equilibrium constants. Okay, so K is we define as a equilibrium constant. K naught is at the standard state. Okay, so if you want to calculate the equilibrium constant at standard state, just exponent the negative delta G naught, okay, 0 divided by RT 0. So this is at standard condition. Standard conditions we consider at 298 Kelvin as 1 bar. So this is for the K naught. Okay, but this one is only for at the standard condition. What happen if depending at different temperature? So we will look at that one later. Okay. So VIGI naught delta G naught standard gives energy change of reaction at equilibrium temperature. So for G naught, actually you can refer to the table C4. Okay. So if you want to do G naught calculations, okay, just refer to table C4 and you can determine K naught. Okay, this one is only at the standard state. Okay, so for examples, this equation, okay, methane plus with H2O, okay, to produce CO and 3H2. Okay, if you want to calculate the standard gives energy change, okay, so we can calculate based on VIGI naught. Okay, this one for each species, H2, CO, CH4, and H2. So this one is products and this one is reactant. Okay. So if you look at table C4, okay. So for hydrogen, hydrogen is element. So there's a no gives energy is equal to 0 times with the stoichiometry. Okay, -1. 1, not -1 times with the, this one is from the table C4 and table C4. So just add all the standard gives energy for each species, you can get total delta G naught. Okay, reacted. Okay, so this is at the standard state. Okay, how what is the influence of the temperature on the equilibrium constant? Okay, what equation that we can use actually? Okay, so actually we cannot use the previous equation because it's only a standard state, but we have additional equations, okay, in addition to the previous equations, so that we can use to the depending on the temperature or the wide range of temperature. Okay, so if we consider the equilibrium constant for the reaction P, okay, K equal to exponent that negative delta G naught divided by RT. Okay, and standard gives energy change. Okay, VIGI naught. So based on the standard properties, actually we can rearrange all this equation to become Van Hoff equation. This is what we call it as a Van Hoff equation. Okay, d ln K divided by dt equal to delta H naught divided RT naught. Okay, so from Van Hoff equations, once we rearrange, okay, to calculate K at T other than the standard state T of 298 Kelvin, okay, let's use Van Hoff equation. This is when you use Van Hoff equation. Okay, so if it is assumed as independent of temperature, okay, not dependent with the temperature, so we can rearrange at the another state of the temperature, at the particular temperature, okay, with the reference of the standard state. So we can get this equation, okay, K1 and K2, K prime, okay. This one is for second state, okay. So from this one we can see, okay, if we rearrange this equation, this Van Hoff equation, okay, so we can get the equation in terms of linear line, okay, y equal to mx plus c. So this is the interception, and this one x-axis, okay, this one x-axis, this one y-axis, and this one is the slope. Okay, so you can get this graph. Okay, we can get this graph actually. So if you want to determine for example equilibrium constant at 1200, okay, at 1200, so just use this graph, okay, for which reaction, okay, for example this one, okay, this one CO, just now is CO, okay, at 1200 Kelvin, so we can get this value, okay, around negative this one 24, so negative 0.02, okay, 0.02, this one is ln K, okay, 0.0 negative, okay. So actually the y-axis you can refer as 1 divided by T or just refer by T in Kelvin. This one is T and this value is 1 divided by T. Okay, this one 1 divided by T. So this is everything, all the equation of all reaction in this graph. So you can refer this graph. Okay, so it's available in the textbook. So if you look at here, that exothermic have a slope positive. Okay, slope positive. So that means this one positive, this is exothermic reaction, and negative, this one, okay, actually is this one is endothermic reaction. K increase with the decreasing temperature. Okay, so we can hear that K decrease with the increasing temperature. Okay, oh slope, K decrease, oh sorry. So this one is positive, right? K decrease with the increasing temperature. Okay, so increasing temperature, so this slope is positive. Okay, this slope is negative. Okay, so exothermic and endothermic. Okay, so what happened to the reactions is not available in this graph. Okay, what happened? How can we determine the K constant or K equilibrium constant? Okay, if not available, because not all the reaction we can obtain from this figure. Okay, so the alternative method is we can use equation. Okay, effect of temperature on equilibrium constant for chemical species in its standard state. Okay, so what you have to do, actually this is the derivation from the Gibbs energy equation. So just substitute the value of delta H naught, delta S, okay, delta S naught. So we can get the final equation to calculate of the equilibrium constant. This is the final equation. So you have to highlight this one. Okay. So if you look at here that is divided into this one is you have to calculate from the equation 4.19. This one is for the Cp for the enthalpy. Right. This one is Cp for the entropy. Okay. So and G naught is a standard heat of reaction. Okay. So this one you can calculate from the table. You can determine from the table. Previously we already discussed this one. Okay, how to determine the delta heat, delta H naught and G naught from the standard heat of formation. Okay, and then you can get standard heat of reaction. So you can determine all this one. You can determine. Okay, so just remember this one in terms of integration. Okay, MCPH or IDCPH, IDCPS and MCP. If you remember IDCPH or MDCPH. Okay, this one is for the enthalpy, and this one or CPS, CPS. This one is for entropy. So we have to determine. Okay, so when you determine the Gibbs energy, okay, just substitute into the previous equation. So calculate ln K. Okay. Okay, actually it's divided into three type of K. Okay, factor of K into three terms. Okay, so K naught, K1 and K2. Okay, so this one is K naught. Okay, this one is K naught, and this one is for K1, and this one is for K2. Okay, so if you look at here that, okay, this one K naught, K1 and K2. K naught is our equilibrium constant for the reference state. Okay, referring for the reference standard state. Okay, this one what we calculate at 298 Kelvin. And this one is the mostly affected by the temperature, the major effect of temperature. This value will be very different with the K naught and K2, because K2 is only small temperature influence. Okay, it's not really affected by the temperature. Okay, by combining all this K, okay, K naught times with K1, K2, so you can determine K. Okay, but the easiest way is you determine G naught, H naught, okay, Cp as well as Cp for enthalpy and Cp for the entropy, and calculate delta G naught and substitute into the equation of ln K. So you can get the value of K. Okay. So this is if you look at here, this one is the expansion of the value of the K2. Okay, combining of enthalpy and entropy. Okay, so how can we evaluate the equilibrium constants? Okay, let's see these examples. Example 5. Okay, if you in the main textbooks. Actually, this is an example of 13.4. Okay. But, okay, so what you have to do is you have to determine value of delta A, delta B, delta C, and delta D, because we want to use this one to substitute into the IDCPS and IDCP PH. Okay, so the meaning of delta is indicate a total of A for C2H H5OH. Okay, minus with the C2H4 and H2O. So product minus with the reactants. Okay, just value of A. Just refer to the appendix C. Okay, and then totals all the value of A, B, C, and D. Okay, for each components. Okay, and then you can calculate delta H naught and also delta G naught at the standard state. How to calculate this one? Okay, all the value of the standard state for delta H naught for each component. For example, this one is for the products. This one is products. This one is for reactant. Okay, so product minus with reactant, you can get total for the delta H naught and also delta G naught at standard state. Okay. Okay, so from the total A, okay, total A, because if you refer this equation, right? So we need this one actually. We need this one. This one. Okay. Delta G naught, delta H naught, or delta H0 G naught. Okay, this one 298, 208 is similar. Okay. And then also we need this one. Okay, this one. So that's why we need to determine all the constants or parameters. Okay. So if you look at here, by using IDCPH and IDCPS, okay, we can determine CP. Okay, this one is for enthalpy and entropy. Okay, please refer back to the chapter 4 and chapter. This one is all the chapter 4 and chapter 6. Okay, how to use this IDCPH and IDCPS. And then you substitute into this equation. If you look at here, that this one, right? Okay, G naught, H naught. This one we calculate from H naught and G naught. This one R T naught 298, value of T. Okay, this one, and this one also H naught. Okay, this one. Okay, at the standard state. This one is enthalpy, CP for enthalpy, and this one for entropy. Okay, this one, this one, this one, and this one. Okay. So once you determine at 488 kelvins, okay, so ln K equal to negative delta G naught over RT. Just exponent this equation so you can get K at 480. Okay. So how about if we increase the temperature to 598 Kelvin. Similarly, okay, by using IDCPH, okay, this one is a standard state. This one is the new temperature. Okay, A, B, C, and D. Okay, so substitute into the equation. This one is delta G naught. Okay, if you look at here, this one, this is this one, this one is this one, this one is this one, and this one is this one. Entropy, enthalpy, this one delta H naught divided by RT, and this one G naught minus delta H naught. Okay, this one is equation for the ln K at the temperature 953. So from all this calculated value, okay, just exponent of delta G naught H. Okay, this one. So this one exponent this value. So you can get value of K. This one is 418 Kelvin. This one is 593 Kelvin. Okay. Okay. And then what you have to do, okay. Similarly, this one is we calculate at 298. Okay, at the standard. We want to see the trend. What happens if we increase the temperature relationship with the equilibrium constant. So this is the summary. If you look at here, that this one is the K naught when we consider only K naught at 298. Okay. So if you look at here, this is the value of K, 29366. When we increasing the temperature to 418 Kelvin, okay, so it's really different. Okay. So influence of K1 is far greater than K2 actually. This one is not so different from the K1. Okay. So the total of the K, it should be this one at for the 480 Kelvin and this one at the 500 Kelvin. So if you look at here, this one is not so much different, right? K2. K2 is not so much different. Okay, this one is K2. Okay, but K1 is much different. The influence is greater for the K1 rather than K2. Okay, so the effect is more to K1. Okay, so that's the effect of the temperature. You can use this equation if the reaction is not available in the figure. Okay, if the reaction is available in this figure or other engineering handbooks, you don't need to use that equation. Okay, so like a previous, I think it's a previous final exam. Okay, I already give this figure. Actually, the direction is available in this figure, but some of students use this method to calculate the value of K. So it's gonna be very long step to determine value of K. Okay, so just make it simplest thing. Okay, if there is a reaction here, just use this figure. Okay, for example, 100, 1500 Kelvin for this reaction and determine log on K. Okay, so you have to check whether your reaction is available in this figure or not. If not available, you can use this equation. Okay, so please remember that one. Okay, so let's we do this one together. Okay. Okay, so tutorial 3. Develop a general equation for standard Gibbs energy change of the reaction delta G naught as a function of temperature for the following reaction. Okay, so how can we determine this one? Okay, can you do? Okay, so what you have to do, you have to apply this equation, this one, because the questions just want to determine delta G naught. This one is G naught divided by RT. Okay, so you have to use this equation. Can you calculate? Okay, by using this equation, I will ask you the answer. So delta H naught plus T, actually it's almost, it's similar actually, because this one is divided by, this equation is divided by RT. Okay, once you divide by RT, this one, you can get this equation and you can calculate K. Okay, it's similar. Okay, so by using this equation, the blue one, can you calculate this one? Please do. What is the temperature? Can you do? Temperature is 298 Kelvin. Okay. (298 Kelvin), the temperature. Okay, so please do. Let me check. Let me check first. Okay, please do by using the previous equation. So I want to know first about the delta H naught and delta G naught. Can you calculate? Delta H negative 92.22. No, delta H not negative 92.22. It's wrong, Animesh. Delta H naught. Okay, this one as standard state, is it delta H naught? Is it this one? Okay. Is it delta H naught? Okay. No. Delta H naught determines negative 46.110. Okay. How about kenapa nak update lecture note? Sama je saya rasa lecture note. Lain ya? Cuma kita tolak je multiple tu. Multiple tu kita tak masuk dengan Duhams. Nanti saya rasa saya tak ada update apa-apa lecture note. Oh, ke saya tak kasih lagi lecture note? Is it I given your this lecture note chapter 13? I've already upload? Oh, okay, sorry. Next time, no next time. It's already final chapter. Okay, I will update the lecture note. I forgot. Next time you remind me. Can you use, let's see, because we want to calculate delta G naught, right? 298. Okay. Delta G naught 298. What's the temperature? Saya tak boleh masuk temperature. So delta G naught at the standard. This one is for function of Can you determine? How about delta G naught? Okay. Delta H naught equal to negative 40, 6, and 1, 0. Okay. Delta G equal to negative 16, 4, 5, 0. Okay. And please determine also delta A, delta B, delta C, and delta D. Okay. So if you determine delta A, delta B, delta C, actually you can refer to problem. Problem which one? I think it's not problem. Okay, I guess you have to calculate this problem. So delta A, B, C, not example. Okay, in this one. So for delta A, B, C, D. So you can get also don't calculate this one. Okay, so just refer to the WhatsApp group. As well as this one. Okay. So please refer to the WhatsApp group. Once you determine delta H, okay, and delta A, B, C, and D. So as well as delta H naught and G naught, you can substitute into equation. But you have to remember you have to calculate IDCPH and IDCPS. Okay, before you substitute to the equation, the last equation. Okay, and you can get the answer. Okay, so the equation is this one. This equation. Okay, so just substitute and you can get the equation. Okay, so that is how to calculate the delta G. Okay. Any questions about that one? About the how to determine K constants? There are two methods I would like to summarize here. First, by using a graph. Okay, is if direction is available in the graph. And second is by using equation. You have to remember that. Okay, but first you have to check. Okay, either direction is available in the graph or not. If available, just use the graph. But if not available, you have to use the equation. Okay. Okay, so let's continue. Okay. Once we determine the K constants, so what is the actually the application of the K constants? Okay. So we want to know the relationship between composition and the K constants. So you have to remember that one because it's going to be affect greatly. Okay. The composition, either it's going to be spontaneous reaction, shift to the right, or it's going to be reversible. Okay. So this is the scope. Okay, the relation of equilibrium constant to the compositions. Okay, and then equilibrium composition of the single reaction. This one we will not cover actually. Okay, this one we will not cover. So we can delete this one because I'm not sure why this semester we not cover. Okay, but for the multi reaction equilibrium actually is quite important. Okay, so just equilibrium composition for the single reaction and the relationship between composition and the equilibrium constant. Okay, let's see the relationship of the K with the conversions. Okay, from the definition of K, okay, K is equal to this one is a sum of the species. Later I will show you, because this is relating with the product and as well as the reactant. Okay, Fi divided by Fi naught. This one is kept Vi. This is a stoichiometry. Okay, let the standard state be the ideal gas state of the pure species at 1 bar. Okay, Fi will be P. So this one is will be P naught. Okay. So once we rearrange the equations, okay, so with the on the left side is the composition and fugacity coefficient, right side with the pressure times with the equilibrium constant. So we can get this relationship. Okay, once you rearrange this equation, okay, by considering all the assumption. Okay, so we can get this. This equation is very important. So you have to remember that if this one is the gas space is not ideal, but if ideals phi I is equal to 1. Okay, so you have to remember what is the meaning of this symbol. Okay, the meaning of these symbols, if you get here from these equations, okay, this one, okay, is going to be if your reaction is A plus B equal to C plus D. Okay, so this equation we can expand sigma C, okay, YC phi, not sigma, phi D YD divided by, okay, this one is for products and this one is for the reactant. A Y A, okay, P B Y B, okay, and this one is I. This one for each species, okay, and then equal to P divided by P naught. This one is total stoichiometry, okay, times with K. So you have to remember that one. Okay, so this one if ideals, so we just use like this. Okay, so this is if ideal. This is if ideal. So how can we determine y? C, y a, y b, and y d. Okay, so you have to remember the previous part. This one is related with this one, extent of reaction, or reaction or order. Okay, so you have to remember this one, and then you substitute this one into this equation, and you have to solve extent of reaction before you get the composition. This is the step. Okay, and we can see the relationship when you increasing pressure or decreasing the pressure. Okay. Okay, so for the gas phase reaction, if the equilibrium mixture is an ideal, this one did already told you. Okay, this one is equal to the pure species. Okay, and it's become 2 to 1. Ideal mixture and low pressure. So this one is for the ideal mixture. This one is for the low pressure. So that means no P. Okay, activity coefficients. And remember, we can express Y in terms of at epsilon. Okay, you have to substitute this one, all this one into here. Okay, this one. Okay, so it's gonna be expand your equation. Okay, because we want to determine the composition. The composition is depending on the extent of reaction, and composition also will have a relationship with the composition with the equilibrium constant. Okay, so let's see the effect of temperature and pressure on the equilibrium constant. So if we have an ideal gas reaction, this one without the P, okay, as well as the Van Hoff equation. Okay, if we combine this equation, let's see the effect of the temperature. Okay, for the endothermic, okay, when if you increase the temperature, okay, the equilibrium constant also increase, and the left side of the equation also increase, this one. Okay, so the composition of the fraction product will be higher. So that means your reaction A plus B product to C plus D. So your reaction will be to the right side, shift to the right. If endothermic, increase in epsilon or external reaction, higher equilibrium combustion. What happened for the exothermic? Okay, for the exothermic reaction, if you increase the temperature, the equilibrium constant will decrease. Left side also decrease, the combustion also decrease. Okay, this one, the ratio. Okay, because the product will be reduced. Okay, so your reaction will be A to B is going to be shift to the left. Okay, shift to the left, more to the reaction. So lower equilibrium constant. So that means this one, okay, is higher rather than the upper side. That's why it's reduced. Okay, this is for the exothermic reaction. Different with the endothermic reaction. Of course, endothermics we have to increase the pressure. Dr. Ho tak perlu darab dengan coefficient. Apa ni? Ho? What is this Ho? H naught. Coefficient? What do you mean by coefficient? What coefficient? H naught. Which one? Yuva. What is the coefficient? Okay. Do you mean the stoichiometry? I think you need to times with the stoichiometry. Okay, the delta H naught. Okay. For okay. For the total stoichiometry number, okay, look at here. If you calculate the stoichiometry number, this one, right? If you remember from this equation, from the previous equation, this one, we have stoichiometry number, right? This one, total. Okay, so we check this one. Okay, if we check, your V is a negative. Okay, so that means when you increase the pressure with the constant temperature, your composition also increase. The product will be higher, shift to the right. Okay, so but if your stoichiometry number, the total stoichiometry number is positive. Okay, so it's going to be shift to the left. This is what the effect of pressure. Okay, with the stoichiometry. Okay, so lower equilibrium combustion. Okay, so for the liquid phase, that one is for the gas phase. Actually, for the liquid phase, if you determine the combustion with the equilibrium constant, what is the relationship? Look at here. Once we rearrange, this is the final equation. Okay, so this is the relationship. Okay, that one is the previous one. The previous slide is just the derivation. This is the, you have to highlight this equation. Okay, so how to calculate the composition? If your solution is ideal, this one is gonna be 1. Okay, similarly, right? So if you look at here that I don't know what it's called. Okay, total xi vi k exponent p not minus p, right? Okay, this is for the liquid. Okay, so actually the exponent term is equal to 1. Generally this part is equal to 1. Okay, so if equal to 1, it's just the parameter of k, except for the high pressure. Okay, if high pressure, you cannot neglect this one, as you cannot consider this one as a 1. So you have to calculate P naught minus P divided by RT times with total VI. So this one is the volume. Okay, so this one is only applicable at the lower pressure or moderate. High pressure, you cannot use this one. So how to determine this gamma? You have to remember chapter 12 by using Wilson equation or Unifax or modulus to determine this activity coefficient. But if ideal liquid solution, this one is equal to 1. Okay, so you have to remember generally for the fraction we use x for the liquid, y for the gas phase. Okay, this one is actually the symbol also you apply in mass energy balance. Okay, y for y composition at the gas, x for the composition at the liquid. Okay, so what time right now? 2:53. You want to stop here? Okay, and then we're going to discuss next week. Okay. So we stop here because I think next week last class we have a test on Sunday, and then Thursday we have a last class. Okay. So next week is gonna be last class. We have a Hari Raya. Okay. So we can finish before Hari Raya as expected. Okay. So please read this one for the single reaction. Okay, what is the effect? It's just the examples we will discuss later. Okay. So any question about this topic?
Doktor.
Ya.
Yang jawapan doktor dekat dalam grup tu, kan ada yang delta G times by 2, yang pertama delta G equals to negative 32,900. Dengan yang delta G yang kedua,
Yang mana?
Itu
yang mana? Example mana?
yang pertama tadi, yang tutorial 3.
Tutorial 3 je. This one. This one.
Ya. Yeah.
Yes. Okay. Kenapa?
Kan delta G yang awal tu kan negative 32,900. Terus yang page 2 itu negative 16,000.
Oh tak. Jawapan the answer is the final answer is delta G not equal to 32,900. This one. This is the answer. I wrote that answer right. Okay. For 16,450. Right. This one is delta G not at 298. Okay. You understand? Based on the reaction, right? If you remember.
Yes.
Okay, so this one is based on this one heat of reaction gives energy enthalpy of reaction and gives energy of reaction, right? N2 plus 3H2 based on this equation. You remember chapter 4? Okay. 2
Yeah.
Okay, you remember, right? Okay. So this one is 0, this one is equal to 0. If 16, okay, calculate 16 450 times 2. Okay, actually you don't have to use. Okay, if you look at here, because this one, right? For me, okay, you don't have to use this equation actually. Okay, because the temperature already told you the temperature of the reaction is at 298 Kelvin, right? Okay, I told you that the temperature is operated at 298 Kelvin. So you can directly calculate. Okay, this one you get negative 16,450, right? So just time with 2. Okay, this one is 2 mole, isn't it? So you can get 32,900. Okay. Okay. So this is the answer. Except if the temperature, the final temperature, or it operated at 100 degrees C. Okay. If operated at 100, if operating temperature is 100 degrees C, so you have to use this equation to calculate delta G. Use this equation. Okay. This one. Okay. This is at what temperature? But if at 298 degrees C or standard condition, just use this equation. Okay. Just direct calculation. Okay. That's another method actually. So it's a fast method because it's just operate at the standard condition. Okay. Okay. Thank you. Who's that? Any question more? Is it clear? Okay. No. Okay. Thank you very much. And please read this example 6 and example 7. Okay. This is important actually. Generally, because I'm gonna prepare the question for chapter 5 for the final. Okay, my question is gonna be like this one. Okay, it's gonna be like this one. Okay, this one. Maybe this kind of tutorial form. Okay, you have to calculate the value of k. Okay, this one. This example, this tutorial. Okay, we will discuss this one. Please try to do this one also. So we will discuss later. My question is going to be like this. The effect of you have to calculate k. Okay, and then you have to determine the composition. How to determine compositions depending on the pressure. What happen if you increase the pressure or decrease the pressure or increase the temperature? Okay, what happened to equilibrium constant, and you have to calculate the composition. That's gonna be my question. My questions. Okay, because I'm gonna prepare this chapter 5 as well as chapter 3 and 4. Okay, for the final. Okay, so I think I hope you can study first, and then we will discuss this one. Example 6, example 7, as well as this tutorial. Please study first. Okay, this one you can refer to the textbook, the 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 example, this example. Okay, okay, thank you very much. Okay, that's all for today. See you next week for the test 2. Okay, okay, saya akan upload.